This is number 22 on the multiple choice. It's probably the apparatus that's giving you some trouble. I think it might be easier to think of this if there were a table there instead of that tube with the string. So the string is connecting little m and big M, and little m is moving in a horizontal circle of radius L. And they're saying that like the student holds the tube and swings the little m around their head. So that's, picture like if you put a ball on a string and swirled it around your head. Okay, so that means you're creating that tension in the string that's keeping the little ball in a circle. But in this thing here, I know we did at least one problem like this from the book where there's like a hole in the table and a heavier mass is hanging down, and that weight provides the tension in the string that makes the block move around in a circle. We'll probably have to remember to review a problem like that. But basically what I've written down here is the formula that we need here. The weight of the big block, or whatever that is, capital MG, is what's causing the little m to move in a circle. So you have our centripetal force, mv squared over r, that's our centripetal force. Well, that's being provided by the tension in that string. So again, the tension in that string is big mg, the weight of that block. And then we can use little m and v squared, but the radius of our circle is that distance L. So the question is, what kind of stuff do we need if we're going to determine the gravitational field strength? So gravitational field strength is little g. So how am I going to measure all those other things? Well, I can measure big M and little m with a balance, okay? And they often call it a mass balance. I don't know what other kind of balance they might talk about. They'll always say mass balance, but they say mass balance. Okay, how am I going to measure this distance L? Well, I can just use a meter stick, or, if they would have said a ruler, then that would have been acceptable as well. And then finally, how are we going to get this V? Well, while it's true that you could use a motion detector to determine the velocity, instantaneous velocity, that's not a choice all on its own. But what you could do, since we're moving around in this circle of radius L, we could figure out the circumference here, right? So we could say 2 pi L for one circumference. And then we could also figure the period of rotation, so we could measure that with a timer. So that would give us the velocity. So the answer to this is C, which is a mass balance, a meter stick, and a timer. Mass balance by itself, that's answer A. That's no good because we need V and L. Mass balance and meter stick are just fine, but we still need a time in order to get velocity. And then, like I said, the motion detector is extra. We don't need the motion detector if we have the balance, the meter stick, and the timer. So the answer to that one is C. 28 is another one that the drawing probably is not helping you. I went over this with Angel in office hours last week, and I think we decided that figure 1 was pretty useless. Basically, this is a tether ball, something hanging from a string at an angle and moving around in a horizontal circle. So figure 2 actually helped me a lot. Figure 1 seemed like it was a combination of a top view and side view, and the more I looked at it, the more confused I got. So let's go with this figure 2, which is mg down and the tension here. So this is the free body diagram on the object at some point. So we're looking for the magnitude of acceleration of this ball, okay? So we're going to use Newton's second law to figure this out, okay? Now the angle here is the angle that the tension makes with the vertical. Okay, we figured this out. I think we just figured that's what they must mean for that. The angle there is the angle that the tension's making with the vertical. So what we know then is if I draw the tension vector here and my theta here, that this here is t sine theta and this here is t cosine theta. So there are my components there. And we need both components for this reason. The y component of tension balances out the weight of the ball. Okay, that's why there's no acceleration in the vertical direction. So because we've measured from the horizontal, the y component goes with cosine. So we get t cosine theta equals mg. And solving for t, we get t equals mg over cosine theta. And if you don't think to do that right away, don't worry about it. It usually comes to you later. Now let's look at the x side. Well, there is a net acceleration in the x direction, and that's equal to ma, which is equal to mv squared over r. Right? Now, what's providing the force in the x direction? Well, it's t sine theta. So t sine theta, and it is mv squared over r, but we don't need any of that information. We're just looking for the acceleration. So we can say t sine theta equals ma. And now, remember, I'm looking for acceleration. So now I can take what I substituted for t over here, and I can say mg over cosine theta times sine theta equals ma. My masses cancel out. My sine theta over cosine theta becomes tangent, and I get a is equal to g tangent theta, which is answer number D. So again, that the drawings were not our friends, but that's how we can explain those. If you want to talk more about them, let me know, but I think you should probably be okay with those. Thanks and take care.